Good day to you. This is David Pye of Pye Metallurgical International Consulting, and today we're bringing some tips to you on retained austenite. And this is for retained austenite through heat treatment courses of Mumbai, and it's in relation to the carburising and carbonitriding course. So, what is meant by retained austenite? The purpose of carburising is to introduce carbon into the surface of a low alloy steel. The reason for this is to create a hard wearing surface with a hardness resistance of approximately 62 Rockwell C scale. The carbon induced into the steel under thermal conditions, and the carbon enters the molecular lattice structure of the steel whilst the steel is in the austenite phase because of the selected temperature. The next stage of the procedure is to rapidly cool the steel and transform the austenite, now present with carbon, into what's known as plate martensite. When the appropriate amount of carbon present in the steel surface and given the correct cooling rate which transforms the austenite, then the austenite will transform from what's known as face-centered cubic lattice structure, that is 14 atoms, into body-centered tetragonal lattice structure, which is 9 atoms. This is now a full martensite in the formed case. However, not everything works in our favour. So therefore, the first potential problem that we can see is that instead of forming plate martensite, we form lath martensite. Lath martensite is formed by not having enough carbon present in the surface of the steel, and we can only achieve a low hardness value. If the appropriate amount of carbon present in the surface of the steel, which is enough to form the plate martensite to give the high hardness value, and yet the cooling rate has been too slow, then we get a mixed microstructure. This requires necessary study of the appropriate time temperature transformation diagram for the appropriate cooling rate. The identification of retained austenite requires very careful investigation and interpretation. The first line of defense would be to check the hardness value of the surface of the carbonized steel. This gives an immediate indication as to either retained austenite is present or that the cooling transformation has been too slow to form the martensite. The cause of the retained austenite and can be attributed to the following conditions. First one, quenching from too high an austenitizing temperature. Second one, quenching into too slow of a quench medium, which is a slack quench. And the third one, excessive carbon in the carbonized steel. The simplest method of dealing with retained austenite is to control the carbonizing and case austenitizing procedure correctly, with very careful control. However, this is not always possible. Cold treatment of the steel consists of exposing the ferrous material to sub-zero temperatures to either impart or enhance specific conditions or properties of the material. Increased strength, greater dimensional or microstructural stability, improved wear resistance and relief of residual stresses are the benefits of cold treatment of the steel. Generally, 1 hour of cold treatment for each 25 millimeters of cross-section is adequate to achieve the results. All hardened steels are improved by sub-zero treatment to the extent that there will be less tendency to develop grinding cracks, and therefore they'll grind much more easily after the elimination of the retained austenite and the untempered martensite. Process temperatures for sub-zero treatment are generally in the region of -75 degrees centigrade right down to -175 degrees centigrade as the optimum temperature for cold treatment. Extended soaking time at a temperature of -175 will improve certain properties beyond the improvement accomplished at the normal average cold treatment temperatures. After cold treatment, it is necessary to temper the components, as you will have transformed the retained austenite into fresh, untempered martensite, which could lead to crack initiation and crack propagation. The early method of cold treatment was to use trichloroethylene with crushed ice as the freezing mixture. Liquid trichloroethylene was poured into a metal container which was placed in an insulated box. The crushed ice, or carbon dioxide, frozen carbon dioxide, was carefully dropped into the trichloroethylene. The trichloroethylene would boil very vigorously until it had reached its coldest temperature. The work was then placed into the liquid and left on the basis of 1 hour per 25 millimeters of cross section. The part was then removed after the soaking time was complete and allowed to warm up naturally to room temperature, and then it was tempered at approximately 170 degrees centigrade. Because of the toxicity of trichloroethylene, a substitute was made, which is perchloroethylene. If that is not available, then simple alcohol / spirits will be acceptable. These methods described are the least expensive methods of cryogenic treatment methods. A present method uses liquid nitrogen to initiate the freezing action. Liquid nitrogen will reduce the process temperature to approximately -170 degrees centigrade. This method does require the capability of storing the bulk liquid nitrogen and having a well-insulated receptacle for the liquid and the component. The current methods are generally in the form of what might seem to be a very large refrigerator. If the components are small enough and you do not have any of the previously discussed methods, a simple domestic freezer will suffice. But the soaking time at that lowest freezer temperature would most likely be doubled. A simple homemade freezer can be used for cryogenic, and the treatment temperature will be approximately -18 degrees centigrade. You can place dry ice on top of the work in the closed insulated container, which is also commonly used for cold treatment. The dry ice temperature is probably about -78 centigrade, but the chamber temperature is generally about -60 degrees centigrade. Mechanical refrigeration units with circulating air approximately -87 centigrade are commercially available. A typical unit will have the following dimensions and operational features in terms of chamber volume up to 2.7 meters cubed, temperature range 5 degrees centigrade right down to -95 degrees centigrade, load capacity about 165 kilograms maximum, and the thermal capacity up to 8,870 kilojoules per hour. Although liquid nitrogen at -195 may be employed, it's used less frequently than any other of the methods because of its cost. In some applications in which explicit amounts of retained austenite are considered beneficial, cold treatment might therefore be detrimental. Multiple tempering rather than alternate freezer temper cycling is generally more practical for transferring of retained austenite in high-speed steels, high carbon, high chromium steels. We trust that this presentation has been a short but useful presentation to you, and the subject of retained austenite and cryogenic has been made a little clearer. It's a very positive method of ensuring that retained austenite has decomposed into fresh martensite. But remember that retained austenite that is present in a carburized case has a different volumetric structure to that of martensite. The retained austenite will then naturally transform into fresh martensite over time, which means you may be out of engineering specification. This means also that there could well be a change in the component size as well as in the component hardness. The surface hardness aspect may well take you outside the initial accomplished hardness and outside of the engineering specification, which could lead to cracking. The course that we're presenting to you, and in particular the carburising course, addresses many aspects of the carburising procedure and its methods, which are based upon practical and theoretical experience by the writer, and we trust that you'll foresee the benefits of advancing your knowledge and becoming a master craftsman heat treater. Yours sincerely, David.